So this is our first discussion about retaining walls. That's going to be the remainder of this class. So the first thing we want to do is just talk about figuring out what the pressure is that's being applied to the walls. And so that takes a little bit of understanding of different types of walls as well. So for example, it turns out that it's helpful for calculations. We can use a lower pressure often if we can allow a wall to move away from the backfill. So if we can let the wall move a little bit, the soil can kind of push on the wall a little bit, maybe get some readjustment, and we can design with a little bit lower pressure. That doesn't work, for example, in a foundation wall or a basement wall. And so it's important to kind of talk a little bit briefly about different types of walls. So in essence, this is a statics problem, and to do the statics calculation, we've got to be able to calculate what the pressure is being applied to the wall. So to do the statics problem, we need to know something about, is this just a huge immovable mass of concrete or stone that's resisting the wall movement? Or are there structural elements that keep the backfill in place? Sometimes structural elements are geometric, and sometimes we just add a lot of extra steel and high strength concrete to keep a wall from breaking. And so basically all of these walls except for the foundation wall, hopefully we can allow some movement. Now if there's something sitting on top of the wall that's important, maybe that's not going to work. But that's something that we'll have to decide. So in general, we're going to be doing the calculations, the statics calculations, based on a two-dimensional infinite length of wall. So we'll be doing this on a per unit length basis. And in addition to the no movement possibility, we'll have two possibilities for movement, either moving away from the backfill or toward the backfill. And so the idea might be that if we were to let this wall move, let's say it's going to move away from the backfill, then we can calculate a reduced pressure on this side, but that also means that it's moving towards the soil on this side. And so we would need to increase the pressure at the toe. Now, sometimes we'll discount that toe pressure for safety reasons. Maybe a utility worker comes along and needs to excavate there. Or maybe during construction, there's some questions about how it will be built. But in essence, that's the problem. So first, we want to take a look at how we're going to calculate pressure. And so in general, we want to think about this idea of K being the ratio of the horizontal to the vertical stresses within the soil. So soil has a strength, and that means that unlike a fluid where pressure's equal in all directions, we're going to have a different vertical pressure than a horizontal pressure. Sometimes I will talk about, instead of H, I'll talk about X, and instead of V, I'll talk about Z. But essentially, that's what we're talking about. So depending on what book you use or how people learned, they may use different variables, but essentially K is always going to be the ratio of the horizontal over the vertical stress. Now, we know how to get the vertical stress. We learned that in fluid mechanics, or we learned it in soil mechanics, and it's just the weight of the soil minus any buoyant force when we're doing effective stress calculations. So the first condition that we talked about is the no movement condition. And in a lot of ways, mathematically, it's a little bit easier to work with, and conceptually, it's probably a little bit easier to work with. And in general, what we're going to describe the no movement condition as is at rest. So, and that at rest is describing the soil. The soil's at rest. It's not moving. It's not moving either away from itself or towards itself. So the at rest condition has a K associated with it, and it's often demarcated as K naught. And so the things that go into K naught are, what's the soil type? What's the construction history? Has there been a great loading and then unloading? Because that can induce a higher horizontal stress than would otherwise have been the case. So for example, for a highly over-consolidated clay, your horizontal pressure can actually be greater than the vertical pressure sometimes. And so here's a case where we can actually take into consideration what the overconsolidation ratio is, and also soil types and the weight of the soil and all those kind of things that we would expect that would factor into the vertical stress also factors into the horizontal stress. So the more interesting case is when we do allow movement. And so the first one that we'll look at is movement away from the backfill. That's going to be called the active case. So there's some vocabulary that we've got to learn about. And so the idea here is that, if this is the wall, it's going to move away from the backfill. Well, it's not that we're grabbing the wall and pulling it. It's really more like the soil starts to expand a little bit, and that pushes the wall. And so we're going to just let that wall move a little bit, which means that we can design with a little bit lower horizontal stress. And we're going to put a factor of safety on this so we know that the wall's not going to just continue to move, but the actual stresses that we'll be designing with will be lower. And so if we are going to go to the fully active condition, that means that soils is actually starting to fail. So we're starting to get failure planes developing within the soil, and it's going to have a certain orientation associated with the friction angle of the soil. So we get a relatively steep angle because the soil is going to support some of its own weight. And the higher the friction angle, the steeper this angle is. And we'll talk about friction angle here in a second. That's a strength parameter. So if we're at the fully active condition and we remember Moore's circle, we talk about how, if we're going to draw out Moore's circle, that the maximum principal stress, that's sigma 1, and the minimum principal stress is sigma 3. So in the active condition, the vertical stress is sigma 1, and that makes the horizontal stress sigma 3. And we're going to come back to seeing some more strength stuff, so we're going to need to learn more. We want to do some examples with this. So the passive condition is sort of the opposite of that. And so for K active, it'll be a case of A, and K passive, it'll be a case of P. And so in the passive condition, we've got a wall that for whatever reason is being pushed, probably externally, it has to be externally, towards the backfill. So the wall is being pushed towards the backfill, and we want to know what the soil pressure is on the other side of that. So in this case, we get something that looks a little bit more like a thrust fault if we were thinking about geology. So we end up with a much lower angle, and that angle is again related to the friction angle. We'll see that in some more circle stuff that I'll show you here in a second. And so what's happening is there's a bunch of little failure planes that are developing within the soil, and if you look closely, these are going in the opposite direction that I drew up above. And so what we're doing is we're pushing on the soil until it starts to fail upwards, and at that point really the soil can't resist anymore. It's actively failing. It's not going to get any stronger as we push it up the hill, and so that's sort of a maximum possible value that we would use. And so we're going to have conservative assumptions built into this, but for now what we're trying to do is just figure out what is the theoretical pressure that would be on the wall in that condition. So in order to do that, we need to know a little bit more about strength. So this is just a quick review of strength. And so in general, what we'll say is anything that's on this side is not possible. And I guess it's probably good to review what the figure is. So this is just one quadrant of Moore's circle. We've got compressive to the right, and soil generally doesn't hold tension, so we're ignoring what's going on to the left on the tension side. And because Moore's circles are symmetric, we can ignore what's going on the bottom. So we can just draw what's happening on the top. And so if we had sigma 1 and a sigma 3 that looked something like this, that would be soil that's considered stable. And so as the deviator stress, the stress between these two increases, maybe it's in the field, or I think the easiest way to describe it now is within load tests. So let's take a look at some load tests, some ways to do soil strength testing. One of them is a triaxial test. And the idea is that we can put a soil specimen in here and separate it from a fluid chamber with a latex membrane. We can pressurize that chamber, and that will pressurize the soil. And then we can add an axial load through the center of that chamber, and we've got some seals to prevent leakage. And so we can test the soil under different confining pressures. And so what we do is we apply a pressure, and so let's say we chose 10 psi. So we would have 10 psi pressurizing the sides where the latex membrane's at, but it's also pressurizing this cap. And so there's a resistance to that is also pressurized from the bottom. And so the soil's under sort of a confining pressure of 10 psi. And then what we can do is we can add a load P, an axial load, that will increase the pressure, sigma 1, along the vertical axis. And we can keep increasing P until it fails. The soil will fail, and we might get a set of failure planes. Maybe we get some cross-hatching, like this thing can kind of start to bow out, and we learn about that in soil mechanics. So the idea would be that our 10 psi might represent this point, and that we could keep increasing the axial stress until our Mohr's circle actually intersects this failure plane. And we would do that several times under several different confining pressures. So instead of 10 psi, maybe we use 7 psi and 5 psi. And with that, we would get different size circles. And that based on different values of P, the deviator stress, we would be able to identify the geometry of this line, and that line represents the maximum possible configuration of shear stress for a given normal stress. And so this is our failure plane, and sometimes it intersects the axis here, and so I'll write out the full equation. So there's the y-intercept. Here's our normal effective stress. And so here we've defined phi prime as the angle of that failure plane. And then the normal stress is the stress that's normal to the failure plane. And I think that the triaxial test is a little bit harder to understand that. But if we take a look at the direct shear test, in this case, we're applying the normal stress through a thing P. So as we increase P, we are increasing the stress on this soil along this dotted line, the plane. And so we'll choose a value of normal stress, P, and then we'll choose, and then what will happen is we'll just start to increase the horizontal stress, which will eventually cause the soil along this specific failure plane to fail. And so we would end up with shear stress along that plane. And that would actually give us a specific point on the plane, on this failure envelope. And this is how it works in the drain condition. So in the undrained condition, and what we'll end up seeing is whenever we have a cohesion term, that some of this starts to get a little bit more complicated, but we're going to ignore the cohesion term for now. I'll show you that here in a second. So what is really happening when the wall moves away from the backfill is that the horizontal stress is dropping and dropping and dropping. So this thing is dropping until it can't get any lower. And once that happens, this thing will intersect the failure plane. And our initial condition was K naught, the at rest condition. And we can even take a look at how this geometry works. So in Mohr's circle, we know that we rotate twice as far as we do in real space. And so there's 90 degrees. This angle right here, due to this geometry, is also phi. And so here's our point that we're going to start rotating from. That's the vertical plane. And then we would rotate 90 degrees. Here's our 90 plus phi, but then we've got to divide that by 2. So we rotate 45 plus phi. So this is 45. This is phi over 2. And that's how we get this angle. That's why we know the orientation of those failure planes. In the passive condition, it's basically the opposite. We'll start at some at-rest condition, and as the wall starts to move towards the backfill, the horizontal stress is going to increase. So it's going to increase and increase and increase, and it will keep increasing as the wall moves closer and closer to the backfill until it reaches a maximum value. The horizontal stress has reached the highest value it can, and all of the soil is failing. And it's being pushed kind of up this sort of thrust fault. And so, again, the geometry for that one is here. Here is, let's get a better color. Here's the vertical stress, and here's 90 degrees. Here's phi. And so in Mohr's circle, that would be 90 minus phi. Or in real space, it would be 45 minus phi over 2. So that's why we know the orientation of that. So now we need to figure out what's the equation to calculate the horizontal stress. And you can do some geometry if you wanted to try and figure this out for the active condition, but someone else has already done that. So if we had a note, so here's, let's call this active. That is equal to the vertical stress times K active. So how do we get K active? Either one of these equations will work. This is just a trig function to transform tangent into sine. I prefer the sine relationship because it is a little bit more intuitive for me. So now we can actually calculate what would the horizontal stress be at any point along the wall. So now it's important to recognize we still haven't really started to work the statics problem, because what we need to do is we need to know what is the stress all along the face of the wall, and then we would integrate that. And it's simple enough to use a triangular pressure distribution because we know that that's going to be the geometry. But for now, all we've talked about is just how to get the horizontal stress at one specific point. We can do the same thing for passive. So for passive, again, we're going to be able to calculate what the horizontal stress is. Here is the equation. And so the difference between the K active and the K passive is that K active, this was a minus, or in this side, these two signs switch. But otherwise, that's how it works. So so remember now, this is only for soils that don't have a cohesion. So this is basically sands and gravels, and if it's like partially saturated, then we can have a suction effect due to the wicking. So what about undrained? So this is clays in the short term. Now in the long term, clays are going to behave a little bit more like this, and that this is one of the most confusing things to try and teach about how clay behaves in the short term versus the long term, or the undrained versus the drained condition. And so when we're talking about drained and undrained, we're not talking about letting water seep out of it. What we're talking about is excess pore pressure that's generated whenever a compression event happens. So if we squeeze clays, the void ratio, the space between the clay particles is decreased. So we're going to say that the clay particles themselves are not compressed, but that the void space between them is compressed. But if those voids contain water, then that water's got to squeeze out, and it takes a while. It just takes a while for that to happen. And so what that means is we can't get things like strength gain or strength loss in the short term. We can get it in the long term. And so in the short term, we can talk about an unconfined compression test. So here are the results for a short-term unconfined compression test. So what that is a chunk of clay gets put into a load frame, and we apply a big load to it, and the soil fails, and we just load it up really quickly. And so that opportunity for volume change hasn't happened. And so what it turns out is we get a phi that's equal to 0, and a cohesion term that we'll describe as SU. So for clays, when we're going to have the wall move away from the backfill, so here we go again, same figures as last time. This is the active condition. And so the wall is moving away from the backfill. And the horizontal stress on a chunk of soil is decreasing. And it's decreasing and decreasing as the wall moves away. Same thing for, so the big thing is that now we don't have an angled failure envelope. Same thing for passive. So we start at the at-rest condition and we increase the stress because now the soil is being pushed towards the backfill, and we get sort of this thrusting action that happens. So the horizontal stress increases and increases up until it reaches a peak value. So how do we calculate those values? Well, it turns out that it has to just do with geometry of a Morse circle. And so if we think about, it's a little bit easier to see for me on the passive side. So if we want to know what is the horizontal pressure, all we've got to do is just take a look at what's the vertical pressure and then add to that. If this is the radius, and the radius is C in this case, we would just add 2 times C. And so on the active side, it would be that we just calculate the vertical stress and then we reduce off 2 radiuses. The last thing we need to talk about is how much soil movement is needed to fully develop either the passive or the active condition. And so what we want to do is think about this axis here as being sort of no stress. So in this case, we've got soil away from the soil mass or towards the soil mass. And if it hasn't moved at all, then we're at the at-rest condition. So P in this case is pressure instead of using sigma. So we start at the at-rest condition, and as the soil moves away from the backfill, as the wall moves away from the backfill, we're going to reduce our stress until we fully develop active stress. And at that point, if the wall moves farther and farther away from the soil mass, we've still got a minimum value. It's not going to go any lower. And so what we really need to know is like, how far, what's this dimension? How far do we have to move away from the soil mass? And so some rules of thumb are developed based on the soil type and the height of the wall. So in this case, H is the height of the wall. And so what you would do is you would look up, do we have cohesionless soil? That would be sands and gravels. Or do we have a cohesive soil that mostly is going to be clays, but sometimes silts? And you can see that there's relatively a small amount of movement needed for a dense cohesionless soil to fully mobilize passive conditions. So the wall just needs to move a little bit away from the backfill to fully develop active conditions for a dense cohesionless soil. But on a soft cohesive soil, so like a soft clay, it actually needs to move a significant amount. And so sometimes we may want to adjust our procedures a little bit based on those things. And then we can see the same thing for passive. Now you can see just from the figure that you've got to move significantly farther away to fully develop passive conditions. And in general, it's almost an order of magnitude. So based on whether or not we can allow the soil, the structure, the retaining wall to move away from the backfill is going to dictate the way that we're going to calculate the pressure. So once we kind of have a feel for, okay, how do we calculate the pressure, then it's just a statics problem, and we're real familiar with those. And so we'll talk more about failure mechanisms, how the geometry might change. So we'll do a sum of forces, we'll do a sum of moments. It becomes a statics problem at that point. So the trickiest thing is, what's the pressure, and can we actually use the at rest or the active condition or the passive condition?